Okay, here's a little problem that will give you some practice in using kinematics. Um, a rock is dropped into a well. It takes 4 seconds after the rock is dropped until the sound of the splash is recorded at the top of the well. How far is it from the top of the well to the water? Okay, well, let's just draw a little picture here of the well. Let's say here's what the well looks like this. And I'm going to put some water here at the bottom of the well. And let's say that the rock starts out right here, is released, and falls down to hit the water. The time it takes for that rock to fall, I'm going to call it T1. And then once the splash is made, the sound waves come back up to the same level, and I'm going to call that time T2. So T1 is the time to drop, and T2 is the time for the sound to get back to the mic, or rather to the place where it can be recorded. Okay, the way to handle this problem, or at least one way to handle this problem, is to realize that as the rock falls, it's undergoing a constant acceleration, g, which is equal to 9.81 meters per second squared. So we can say that it covers the distance from the top of the well to the bottom of the well, which let's call that h, that distance h. H is equal to 1/2 g T1 squared. That's because it started out at 0 velocity and fell at a constant rate. So then we can also say that once the sound is made, it travels back up the distance h, and that's equal to the velocity of sound times T2, the amount of time it takes for the sound waves to make it back up to where the rock was dropped. The total amount of time that it took is T1 plus T2. In other words, T1, I'll put it over here, T1 plus T2, and that's equal to 4 seconds. I'm just going to write down a 4 because that's easier to write than just introducing another variable. So how do we solve this problem? Well, first of all, we have these two equations right here that connect T1 and T2, and this equation that connects T1 and T2. So a simple way to do this would be to say that these two are equal. In other words, 1/2 g T1 squared is equal to velocity of sound, Vs, times T2. But from this equation over here, we can say that T2 is equal to 4 minus T1, and then we can stick that right in here and write this as 1/2 g T1 squared is equal to V sub s times T2, which is 4 minus T1. So now we have an equation just involving the variable T1, and we know the other things. I didn't tell you, but the velocity of sound near the surface in air is approximately equal to, say, 343 meters per second. So all we have to do is solve this equation for T1. And then we can either plug T1 back into this equation to get what H is, or we can solve this one for T2, plug it in here, and get what H is. So first of all, let's deal with this. This is a quadratic equation, and I can write it in the form of a standard quadratic equation by moving the stuff on this side of the equation over here. First of all, let me just write that out. This is equal to 4 times Vs minus Vs times T1. So moving these two factors over to the other side of the equation, I can write it like this: 1/2 G T1 squared plus V sub S T1 minus 4 V sub S equals 0. Now this is in the standard form, ax squared plus bx plus c, and we have the quadratic formula to solve that. Let me move it up a little bit here so we can see it a little better. So I'm going to say then that T1, which corresponds to the x, T1 is equal to minus b, but b is equal to v sub s. So I'm going to put v sub s plus or minus square root of b squared, which is v sub s squared, minus 4. And I always do it like this. I put in a space to put in what a is, and leave a space here to put in what c is. A is equal to 1/2 g, so I'll put that in there, 1/2 g. And c is equal to minus 4 Vs, so I'll put that in there, minus 4 times Vs, and all of this is over 2a, which is 2 times 1/2 g. So I can do a little bit of simplification here to make it a little nicer. 2 divided by 2 is 1, so I can just scratch those out. And 2 into 4 gives me 2. So I have 2g times v sub s times 4 with a minus sign in there. Let me write this down one more time, make it a little simpler here. This is equal to minus v sub s plus or minus the square root of v sub s squared. Let's see, a minus times a minus is a plus. 2 times 4 is 8, so I have plus 8 from that term and that term, times g from that term, times v sub s. And all of this is over g. So now I can plug in the numbers and write this as, this is equal to minus the velocity of sound, or the speed of sound, 3, 4, 3, plus or minus the square root of 3, 4, 3 squared, plus 8 times g, which is 9.81 meters per second squared, times 343. All of this is divided by g, which is 9.81. So we're going to plug those numbers into the calculator. Okay, so I moved this up out of the way so I can get my calculator in view here. And let me get it up here. And I'm going to clear all that. And I'm going to try to calculate what's under the radical first. So I'll put in 3, 4, 3, square that, plus 8 times 9.81 times 343 equals, that's everything that's under the radical. Take the square root of that, and I get 380.22 plus some extra digits. So let me write that down. This is approximately equal to minus 343 plus or minus 380.22 plus some extra digits, and all of that is over 9.81. So first of all, take a look at this. I have a minus sign here and a minus sign here. Obviously, if I add those together, I get a minus divided by a positive, leaves me with a minus, and I can't have a negative time, so I have to take the plus sign here. So 380.22 minus 343 equals 37.22 plus some digits divided by 9.81 equals, and that comes out to be about 3.79 seconds, approximately 3.79 seconds plus some extra digits. And I'm just going to store this in one of my memory locations just to use it later. So that's how many seconds it takes to fall to the water. Okay, so I want to use this to figure out what h is, and I know that h is equal to 1/2 g times t1 squared, so that's equal to 1/2 times 9.81 times 3.79 plus some digits squared, and that's equal to approximately, let's see, here's my 3.79 seconds. If I square that times 9.81 divided by 2, that's equal to 70.609. Let's call that approximately 70.61 meters. And that's the answer. And that's about equal to, using 3.28 feet per meter in here, that's about equal to, let's multiply this times 3.28, and that's about 232 feet, approximately 232 feet. That's a fairly deep well. Now, alternatively, we could have calculated T2, and remember we had T1 plus T2 is equal to 4 seconds. And that means then that T2 is equal to 4 seconds minus T1. So that's equal to 4 seconds minus 3.79 seconds, which is approximately equal to, let's go back and retrieve that 3.79 seconds. Subtract 4 from that and then change the sign. So that's 0.2058 seconds, 0.2058 plus some extra digits. So then h is also equal to the speed of sound times T2. So that's equal to 343 times 0.2058. And that's approximately equal to, okay, times 343 equals, and lo and behold, that's equal to 70.61 meters. Same thing. And that's one way to solve this problem.